Okay, so here we have quiz 2, and this first problem is a Thevenin problem. I can tell that because it says draw the Thevenin equivalent circuit. So if we recall, all Thevenin equivalent circuits look like one voltage source, one load resist, so one Thevenin resistor and one load resistor. R load, R Thevenin, E Thevenin. Can also be called the V Thevenin, right? And this is an equivalent. So what that's saying is that everything inside of this red box up here could be simplified and redrawn as an equivalent right here. Just like if I take two resistors that are in series and then I put them together as one equivalent resistor, well, now I've taken an equivalent circuit. Everything inside that pink box can be modeled as a Thevenin resistance and a Thevenin voltage. Solving for each of these is two separate steps, often helpful to redraw, but you don't have to. So when solving for V Thevenin or E slash V Thevenin, right? We remove the load. So here's A, here's B, and then everything else in the circuit stays the same. I'll draw it the way it's drawn, although it doesn't have to be as long as I keep my node connections the same. Right, so here's 15 volts, 1.5, 1.5, and 1.5. And what do I mean by it doesn't have to be drawn that way? Well, if I wanted, I could take this resistor that's in as a diagonal right here, and it could also be drawn like this. It wouldn't matter because either way, on the outside of it, it is connected between A and B, just like the other 1.5 resistor. The other node that I have, we'll call it C. Node C up here. So we have A, B, and C. In this open node voltage, VAB, that is our Thevenin voltage, the open node voltage. So the way that I'm going to do it is that I see that these two resistors are in parallel. So I'll combine them. Two equal resistors means I can do 1.5 divided by 2 is 0.75. And if I wanted to redraw it again, I could. Right here, 0.75. I'm still looking for the open node voltage, and I have 15 volts. Well, now I see that 1.5 and 0.75 are in series. So for me, the fastest way to do that is VDR. Vx equals V equivalent. What is the voltage being shared amongst series resistors? Well, 1.5 is in series with 0.75. I'm searching for the value across the 0.75. Actually, before I do that, I'll write the equation just so that we're clear on all parts of the equation. Rx over Req. So the VEQ, the voltage being shared, is 15 volts between those series resistors. I'm looking across the 0.75 resistor, and 1.5 plus 0.75 comes out to 5 volts. So on my Thevenin circuit over here, the Thevenin voltage is 5 volts. So that is for my Thevenin voltage. Now for my Thevenin resistance, R Thevenin, once again, it's helpful to redraw. And I'm going to open those nodes, remove the load, and put the circuit back, except I'm going to zero the source. 0 volts is a wire, because if I'm looking at these green dots from this dot to this dot, there's no voltage change. 0 volts from each of those dots, whereas before there was 15 volts across them. Well, now there's no voltage change there. We can look at our nodes. I'll label it in green. Here's one node right there. And then starting right here, look, it goes up there, and now this node goes all the way around because I've shorted it. That's what a short does. And so I have two nodes, A and B, and it's like I've connected an ohm meter there, right here. There's an ohm meter that's measuring the total resistance between them. Another way to write that is to put an arrow with an R, right? So that R is looking back at that whole circuit. Well, they all three share the same two nodes on the outside, so they're in parallel. 1.5 in parallel with 1.5 in parallel with 1.5. Well, they're all equal, and there's 3 of them, so I divide by 3. Comes out to 0.5 ohms. And right here, this R Thevenin is equal to 500 ohms. That was 0.5 kilo ohms is the same as 500 ohms. And there is, I've now calculated and drawn my Thevenin equivalent circuit. So everything inside my yellow box, that is my final answer. For the voltage, there's probably 4 obvious to me, 4 different ways to do this. There's probably even more than that. There's always more than one way to solve for these circuits. And all we're told is to calculate the voltage at node A. So let's identify first, what is node A? All of this is node A. And what I'm searching for is the voltage at A. I'll solve it first with nodal analysis because that's how a lot of students would think, especially if it says if using nodal analysis, you must write the equation. So the next step would be to label all our nodes with a reference node. That reference node is VB. The reference node is ground, 0 volts. Everything inside of this, all of this, all has 0 volts. There's no element, there's no voltage drop across it. It's all 0 volts, everything inside those wires. There's one more node right here, VC. And notice that it is not positive 20 volts, it's negative 20 volts because I'll highlight in yellow right here, that is the low side. This is the high side. So if VB is the ground floor, then I go down to get to VC. I'm going from the high side to the low side. So VC is negative 20. The next step in Kirchhoff's, nodal analysis is Kirchhoff's current law. I'm going to draw all 3 arrows going out because it's just too easy. They're all right there. In KCL, says what goes in must come out. Well, nothing's going in, so that's 0. And I have I1 plus I2 plus I3. 1, 2, and 3. It's probably helpful to label I's to make sure you don't start plugging in 2 amps. This is an I1, I2, I3. I1 is equal to VA minus VB over 300. If you just thought, why is it VB? Why isn't it ground? Isn't it connected to ground? Well, VB is ground. So this is 0. So if you just wrote VA over 300, that would also be fine. I2, once again, is VA minus VB over 600. VB is once again the reference node. It is ground. Everything inside of B is 0. So it's VA over 600. I3 is going from VA to VC, from tail to tip. VA minus VC going across a 200 ohm resistor. I know VC is negative 20. So I could write VA plus 20 over 200. Plug all those in. 0 equals VA over 300 plus VA over 600 plus VA plus 20 over 200. And from here, you can do algebra, multiply everything by 600 if you want. You could also do numsolve in the calculator where we use X as the unknown for VA, and then it spits out VA equals negative 10 volts. That is a way to solve for VA. Another way, and I'll start up here, I'll write this one in orange, is if I had this circuit and I wanted to combine my 300 and 600, right? REQ. 600 is in parallel with 300, right? They each share A and B on the outside. Well, 600 and 300 together makes 200 equals 200 ohms. This one is also 200 ohms. So that means if I have 20 volts and I'm looking at what goes up must come down for Kirchhoff's voltage law, or if I wanted to do a voltage divider rule, I can basically analyze this without even mathematically doing it by just do it in my head. 200 ohms and 200 ohms are equal. They each share 20 volts, which means they each have a 10 volt drop across them, right? And so if the current is flowing in out of this way and it goes down and then down again, I know that this point is ground. So if there's a 10 volt drop across this, VA must be negative 10 volts. It's negative 10 because it's 10 below the ground. The current is flowing out of the positive end of the battery. So this is the high side and that's the low side. This is the high side and that's the low side of that resistor. VA is 10 volts. Another way to do it, and I'll pull it down here and do it one more time, is if I had these right here and my battery, oops, in this direction. Here's my ground, 220 volts, 600 and 300. And if I wanted to do a source transformation, I have a voltage source in series with my resistor. So another way to do this, V equals IR. When I'm doing source conversion, I'm looking for the one next to the source. So IS is going to be V over R, which is 20 divided by 200, and IS equals 100 milliamps, which is the same as 0.1 amps. So redraw, and now I have arrows going down, right? It's going down because the plus of the 20 volts is going down. And so I have 100 milliamps. And then I have each of these, 200, 600, 300. If I wanted, I could do a current divider rule from here. Not necessary if I wanted to also combine everything and put the 300 is in parallel with the 600 is in parallel with the 200. We already said earlier that this comes out to 200 parallel to 200. Those are equal, and it comes out to 100 ohms. So final circuit, 100 ohms, 100 milliamps. And now if I'm looking at what is the voltage across this, well, 100 milliamps, 100 ohms gives me 10 volts. 10 volts is across this resistor. Here's the high side, here's the low side, which means that VA, what this right here, we'll call it the voltage across the resistor, right? And that's the current going through the resistor. But the VA here is negative 10 volts because it's 10 below ground. And once again, we get to negative 10 volts. There's more ways to do this with current divider rule and other laws, but I think that's enough for how most of us are going to solve this problem.